Hello there, and welcome back to Bedtime Science. I'm really glad you're here tonight. Tonight, we are going to listen to a planet that almost never appears to move. The floor is steady. The walls are quiet. A glass of water can stand undisturbed on a table. And yet, far below this peaceful surface, continents are traveling. Ocean floors are being made and destroyed. Mountains are rising. Iron is flowing around a solid inner core, and rock that seems immovable is bending with the patience of geological time. Every volcano and every earthquake begins inside that contrast, a surface that feels still, and a planet that has never truly stopped moving. Volcanoes and earthquakes can sound like subjects built entirely from danger. They are real natural hazards, and nothing in their science asks us to forget that. But fear is only the loudest part of the story. Beneath it lies something larger and more surprising. The same internal heat that melts rock and loads faults also creates new seafloor, recycles old crust, raises mountain chains, feeds mineral-rich springs, builds islands, and helps move carbon between the deep earth and the atmosphere. A restless planet can be hazardous, but its restlessness is also part of what made Earth the world it is. So tonight, rather than rushing from one disaster to another, we will follow the hidden system itself. We will begin beneath the crust, where earthquake waves reveal layers no human has ever seen. Then we will drift with the plates, descend into ocean trenches, rise with magma, cross black lava fields, listen to volcano observatories, and watch the ocean respond to a sudden movement of the seafloor. Along the way, there will be ancient cities, new islands, magnetic stripes, buried forests, warning systems, and rocks that carry messages from depths we cannot reach. The ground may be quiet now. That makes it a good time to understand what it is quietly doing. The first calming correction is that Earth is not simply a ball of molten rock beneath a thin crust. The image is tempting, but it is wrong in an important way. The mantle is hot, and over long intervals it can flow, but it is mostly solid rock. It moves not like water, but like something so viscous that ordinary experience has no good comparison. A solid can deform if temperature, pressure, and time are large enough. The deep earth teaches that solid and motion are not opposites. The crust is thin compared with the planet, yet it carries almost everything familiar. Cities, forests, farms, oceans, roads, rivers, and sleeping rooms all exist on a shell that is tiny beside Earth's radius. Oceanic crust is usually only a few kilometers thick. Continental crust is thicker, lighter, and more complex. Beneath both lies mantle rock, and below that lies the metallic core. The familiar world rests on layers that differ in chemistry, density, temperature, and behavior. The outer core is liquid iron alloy, moving slowly enough to be hidden and powerfully enough to generate Earth's magnetic field. The inner core is solid, not because it is cool, but because pressure is immense. This is one of the strange, quiet facts of deep Earth science. Temperature alone does not decide whether a material is solid or liquid. Pressure matters too. At the center of Earth, iron can remain solid even at temperatures comparable to the surface of the sun. Seismology made these hidden layers visible without anyone traveling there. Earthquake waves cross the planet and change speed, direction, and character as they pass through different materials. P waves can move through solids and liquids. S waves need material that can resist shear, so they cannot pass through the liquid outer core. The absence of S waves in particular regions became one of the great clues that Earth's core is partly liquid. The planet was read through its own vibrations. There is something restful about that idea. The Earth reveals its interior not by opening itself, but by ringing. A distant earthquake sends waves through rock. Instruments record the arrivals. A pattern appears, faster here, slower there, blocked here, bent there. From those motions, scientists infer layers, boundaries, slabs, plumes, and core structure. The deep Earth is not directly visible, but it is not completely hidden. It speaks in waves. Imagine one earthquake beginning beneath an ocean on the far side of the world. The rupture lasts only a short time, but the waves it releases take many different routes. Some skim near the surface. Some pass through the mantle. Some bend around the core. Some disappear where liquid metal refuses to carry shear. Hours later, instruments across the planet hold a pattern of arrival times. No drill has crossed the mantle, and no camera has photographed the core, yet the earthquake has briefly illuminated the entire interior. This is one of geology's most elegant reversals. An earthquake is usually described as something that hides structures beneath damage and noise. In seismology, the same event becomes a lamp. The shaking contains information about every material it crosses. A wave speeding up suggests one kind of rock. A wave slowing or bending suggests another. A missing wave may be as informative as one that arrives. Earth has no window into its center, so scientists learn to use echoes. One of the most beautiful examples began with waves that seemed to have arrived where they should not have been. In the early 20th century, seismologists already understood that the liquid outer core created a broad shadow in which certain direct waves were difficult to detect. The pattern made sense, but it was not perfect. A few faint arrivals kept appearing inside the shadow, like quiet footsteps in a room believed to be empty. In 1936, the Danish seismologist Inga Lehmann considered those unexpected waves. She had spent years working with earthquake records, comparing the precise times at which signals reached stations around the world. The paper traces were delicate, and the instruments were far less sensitive than modern digital networks. Yet Lehmann recognized that the strange arrivals could be explained if the center of Earth was not entirely liquid. A solid inner core could reflect and bend some waves back into places where a simpler model predicted silence. It was a discovery made without a dramatic expedition. There was no descent through the crust, no sample lifted from the center, and no photograph of iron under impossible pressure. There were only earthquakes, instruments, numbers, and a mind patient enough to notice that the silence contained an exception. Later observations confirmed the basic picture: a liquid outer core surrounding a solid inner core. The story has an appealing geological symmetry. The smallest marks on paper revealed one of the largest hidden objects inside the planet. A faint wave, after crossing thousands of kilometers of rock and metal, carried evidence of a sphere more than 2,000 kilometers across. Deep Earth science often works this way. The signal may be tiny, but the structure that created it can be immense. Today, researchers listen even more closely. Some study how waves move differently through different parts of the inner core. Others investigate whether the inner core rotates at a slightly different rate from the mantle above, or how its crystals may be aligned. The broad architecture is known, but the center of Earth remains a place of active questions. The planet has allowed us to map its deepest layers, while still keeping enough mystery to reward every improvement in listening. Plate tectonics gives volcanoes and earthquakes their larger frame. Plates are not floating freely like boats on a pond. They are rigid pieces of lithosphere interacting with the hotter, weaker rock beneath and with one another at their edges. Where they separate, new crust can form. Where they collide, crust can buckle, thicken, or sink. Where they slide past each other, faults can store stress. The map of earthquakes is largely a map of plate boundaries. The motion is slow enough to feel imaginary until it is measured. A few centimeters per year is the speed of a fingernail, a slow route, a quiet drift. But over 10 million years, a few centimeters per year becomes hundreds of kilometers. Oceans widen. Continents migrate. Island arcs grow. Mountains rise. The planet does not need speed to transform itself. It needs persistence. For a long time, The slow travel of continents was one of science's most uncomfortable ideas. In 1912, Alfred Wegener pointed to a pattern that seemed almost too obvious to ignore. The coastlines on opposite sides of the Atlantic looked as though they might once have belonged together. Matching fossils appeared on continents now separated by thousands of kilometers of ocean. Mountain belts and rock layers continued from one shore to another as if the Atlantic had cut through an older landscape. Wegener's evidence was intriguing, but his explanation was incomplete. He could describe the journey without showing a convincing engine. Continents, many geologists argued, could not simply plow through oceanic crust. So the idea of continental drift waited for other discoveries. Maps of the seafloor, chains of earthquakes descending beneath island arcs, heat rising at ocean ridges, and symmetrical magnetic stripes preserved in basalt. By the 1960s, the missing mechanism was becoming visible. Continents did not travel alone through fixed oceans. They rode on plates, and the ocean floor moved with them. The story is useful because it shows how a scientific revolution can feel before it becomes obvious. The clues may already be present, but they do not yet belong to one picture. Then a new framework arrives, and earthquakes, volcanoes, trenches, ridges, mountain belts, fossils, and magnetism begin to fit together. Plate tectonics did not merely add one more fact to geology. It gave the planet a grammar. Divergent boundaries are places of beginning. At mid-ocean ridges, plates move apart and mantle rises beneath them. As pressure decreases, mantle rock partly melts, producing basaltic magma. That magma cools into new oceanic crust. The ocean floor is therefore not ancient everywhere. It is continually created at ridges and carried outward like a slow conveyor. The floor beneath the sea is a record of motion written in rock and magnetism. Basalt formed at ridges is dark and dense. It can erupt as pillow lava underwater, forming rounded shapes as molten rock meets cold seawater and chills quickly on the outside. Each pillow is a small record of lava entering water. Seen in sequence, pillow lavas can look almost soft, though they are stone. They are the shapes of heat meeting ocean. The mid-ocean ridge system is mostly hidden from human sight, but it is one of the largest features on the planet. It winds through the oceans for tens of thousands of kilometers, a global seam where the Earth quietly renews its outer skin. Most volcanic activity on Earth is not a cone rising above land. Much of it happens beneath water, in darkness, where new crust forms without headlines. Iceland is special because a ridge rises into air there. The Mid-Atlantic Ridge crosses the island, and the Iceland hotspot adds extra heat and magma. This makes Iceland a place where the creation of oceanic crust becomes visible as land. Cracks open, lava flows, steam rises, new rock cools under weather. A process that usually belongs to the seafloor becomes a landscape of moss, ice, black sand, and glowing eruption fissures. The ridge system that creates oceanic crust stretches for roughly 65,000 kilometers through the world's oceans. It is the longest mountain chain on Earth, though most of it lies beyond ordinary sight. Along its crest, cracks open, basalt erupts, seawater circulates through hot rock, and new seafloor begins its outward journey. The most extensive volcanic landscape on the planet is therefore not a dramatic line of cones on land. It is a hidden seam running through the darkness beneath the sea. Convergent boundaries are places of return. Oceanic lithosphere grows colder and denser as it ages. Eventually, at some margins, it sinks into the mantle and subduction zones. The ocean floor that formed at a ridge can end its surface journey by descending beneath another plate. In this way, Earth recycles its crust. The seafloor is born, travels, cools, bends, and returns downward. Subduction creates some of the most powerful geological systems on Earth, because water changes the chemistry of melting. The descending plate carries minerals, sediments, and water into depth. As water is released, it lowers the melting temperature of mantle rock above the slab. Magma forms, rises, and feeds volcanic arcs. This is why many dangerous volcanoes stand above subduction zones, from the Andes to Japan, from Indonesia to the Cascades. Transform boundaries are places of sideways patience. Two plates move past each other, but roughness locks parts of the boundary. Stress accumulates. Rock bends elastically, then a locked patch slips, and the stored energy becomes an earthquake. The plate motion was slow, but the release can be sudden. This is the elastic rebound idea. Rock can behave like something springy when seen across the right timescale and stress. California offers a familiar example of this sideways patience. The San Andreas is often drawn as a clean line, but on the ground it belongs to a broad network of faults carrying motion between the Pacific and North American plates. In some places the fault creeps. In others it is locked. The plates continue moving even where the fault does not, so the surrounding rock stores elastic strain. In 1906, a long section of the San Andreas ruptured near San Francisco. Fences and roads were offset, the ground shifted by meters in places, and shaking was followed by fires that caused much of the city's destruction. The lesson was not simply that a fault can move. It was that a city experiences an earthquake through many interacting systems: soil, water lines, buildings, roads, fire, and human decisions. The rupture lasts moments. Its consequences travel through everything built above it. Faults have different geometries, and each geometry tells a story. Normal faults form where crust stretches. Reverse and thrust faults form where crust compresses. Strike-slip faults form where blocks slide sideways. Many real faults are combinations of these motions. A fault is not simply a crack. It is a surface across which rock has moved, sometimes many times, sometimes through many earthquake cycles. Earthquake magnitude and earthquake intensity are not the same. Magnitude describes the size of the earthquake itself, the energy released by fault slip. Intensity describes what shaking feels like and what damage it causes at a particular place. A large earthquake far away may be felt gently. A smaller earthquake shallow beneath a city may be damaging. The experience at the surface depends on depth, distance, geology, building design, and duration. Soft sediments can turn shaking into a longer, stronger motion. Bedrock and loose water-rich ground do not respond in the same way. Sediments can amplify waves, trapping and lengthening shaking. Liquefaction can occur when saturated sandy soils lose strength during shaking and behave temporarily like a fluid. This is why two neighborhoods in the same earthquake can experience very different effects. The ground beneath a building is part of the hazard. Engineering is the quiet human answer to seismic reality. Earthquakes cannot be prevented, but buildings can be designed to move without failing catastrophically. Flexible frames, shear walls, base isolation, dampers, better foundations, and thoughtful land use planning all transform knowledge into safety. The goal is not to overpower the earth. The goal is to understand motion well enough that structures can ride through it. Earthquake early warning is different from earthquake prediction. Prediction would mean knowing the time, place, and size of a future earthquake before it begins. That remains beyond current science. Early warning begins after an earthquake has already started. Instruments near the rupture detect fast-arriving waves and send alerts before stronger shaking reaches more distant places. Seconds can matter. Trains slow, surgeries pause, elevators open, and people take protective action. The size of an earthquake is easy to underestimate because the familiar magnitude scale is logarithmic. A magnitude 7 is not just a little larger than a magnitude 6. Each whole number increase represents about 10 times the measured wave amplitude, and roughly 32 times the energy release. The compact number hides an enormous change in physical scale. Modern seismologists usually describe large earthquakes with moment magnitude, which is tied to the fault itself, how much area slipped, how far it moved, and how rigid the surrounding rock was. The largest earthquake measured instrumentally occurred in Chile in 1960 and reached magnitude 9.5. The rupture changed coastlines, sent a tsunami across the Pacific, and made the whole Earth vibrate in modes too low for human hearing. In 2011, the magnitude 9.1 Tohoku earthquake in Japan revealed how dramatically a subduction fault could slip near the ocean trench, generating a tsunami that exceeded many expectations. These records are sobering, but they also reveal why great earthquakes are concentrated in certain places. A subduction boundary can remain locked while plates continue converging for decades or centuries. The edge of one plate is slowly drawn downward. The overriding plate bends. Then a great section of the boundary releases. The earthquake is sudden, but the energy was gathered almost invisibly, year after year, at the speed of plate motion. Aftershocks are not random punishment after a main shock. They are the crust adjusting to a changed stress field. Most aftershocks are smaller than the main event, and their rate usually declines with time, though the sequence can last for weeks, months, or longer. The Earth does not instantly settle after a large rupture. It relaxes through many smaller slips, like a strained system finding a new arrangement. Sometimes faults move without a large earthquake. Slow slip events release strain over days, weeks, or months, too gently to produce strong shaking. They are especially important in subduction zones, where they reveal that a plate boundary can slip in more than one style. The boundary is not either locked or rupturing. It can also creep quietly, shifting stress in ways that scientists are still working to understand. Deep earthquakes add another mystery. Most earthquakes happen in the brittle outer shell of Earth, where rock can fracture. Yet earthquakes also occur hundreds of kilometers down within subducting slabs. At those depths, pressure should make ordinary brittle failure difficult. Several mechanisms have been proposed, involving mineral transformations, dehydration reactions, and instability within cold descending slabs. Deep earthquakes remind us that even familiar processes become strange under the conditions of the mantle. Volcanoes begin with melting, but not all melting is the same. At ridges, melting can happen because pressure drops as mantle rises. At subduction zones, melting can happen because water changes the melting behavior of mantle rock. At hotspots, unusually hot mantle may rise from depth and produce melting beneath a moving plate. These different beginnings create different magmas, and different magmas create different volcanic styles. Magma is not simply liquid rock. It is a mixture of melt, crystals, dissolved gases, and sometimes bubbles. Its behavior depends on temperature, chemistry, crystal content, and gas. Silica-rich magma tends to be more viscous, resisting flow and trapping gas. Basaltic magma tends to be less viscous, allowing gas to escape more easily and lava to flow farther. The personality of a volcano begins in the chemistry of its magma. Effusive eruptions can be quiet in the geological sense, though still dangerous to property and landscapes. Lava may flow from vents, channels, tubes, or fissures, glowing at first and then darkening as a crust forms. The front advances slowly compared with human running speed in many basaltic flows, allowing evacuation. Yet lava is relentless. It can bury roads, farms, forests, and homes, creating new land while covering old land. Pahoehoe lava forms smooth, ropey surfaces as fluid basalt moves beneath a cooling skin. Aa lava forms rough, jagged blocks when the flow is cooler, more viscous, or more disrupted. These Hawaiian words name textures that record movement. A lava surface is not only a surface. It is the frozen memory of how molten rock traveled. Lava tubes are natural tunnels made when the outside of a lava flow cools and hardens while molten lava continues to drain through the interior. After the flow empties, a hollow passage remains. Some tubes can stretch for long distances, preserving a record of old eruptions and offering pathways for lava during active flows. On the Moon and Mars, possible lava tubes are studied as shelters and clues to volcanic history. Explosive eruptions come from trapped gas and resistant magma. As magma rises, pressure decreases, gases expand, and bubbles grow. If the magma is too viscous for gas to escape gently, pressure can build until the magma fragments into ash, pumice, and hot gas. The eruption column can climb into the atmosphere, spreading ash over wide regions. The violence is not arbitrary. It is physics, gas expanding inside a resisting melt. Volcanic ash is not soft household ash. It is often made of tiny fragments of glass, crystal, and rock. It can travel far in wind, affect aircraft, darken skies, damage machinery, contaminate water supplies, and burden roofs. Yet ash also becomes part of future soil and sediment. Like many volcanic materials, it has two stories: immediate hazard and long-term transformation. Pyroclastic density currents are among the most hazardous volcanic phenomena. They are hot mixtures of gas, ash, and rock fragments moving quickly under gravity. Here, it is enough to understand them as clouds of heated volcanic material that hug the ground and move with great speed. They show why evacuation zones around explosive volcanoes matter. Some hazards cannot be outrun once they begin, so monitoring and planning happen before they do. Lahars are volcanic mudflows, created when ash and loose volcanic debris mix with water. The water may come from rain, melting snow and ice, crater lakes, or river systems disturbed by eruption. Lahars can move down valleys far from the volcano, sometimes long after the eruption that supplied the loose material. A volcano's hazard is therefore not limited to the cone itself. Valleys, rivers, and weather all become part of the system. Shield volcanoes are broad and gentle in shape because fluid basaltic lava can travel long distances before cooling. The Hawaiian volcanoes are classic examples. Stratovolcanoes, by contrast, are steep cones built from alternating layers of lava, ash, and fragmented material. They often form at subduction zones and can erupt explosively. The shape of a volcano is a biography. It records magma type, eruption style, and tectonic setting. Cinder cones are smaller and simpler, built from fragments ejected around a vent. Lava domes form when very viscous lava piles up near the vent rather than flowing far away. Calderas form when a volcano loses enough magma from a shallow reservoir that the ground above collapses. These forms are not decorative labels. They are clues to the movement of magma and the history of eruptions. A cinder cone may sound like an ancient feature, something a landscape inherited long before people arrived. Yet in the 20th century, farmers in Mexico watched one begin almost from nothing. The place was a cornfield near the village of Paracutan, in a region where older volcanic cones already dotted the horizon. The ground had been restless for weeks, with earthquakes felt across the area. Then, on February 20th, 1943, a crack opened in the field. The first signs were small enough to seem almost uncertain. A depression, rising dust, dark smoke, and the smell of sulfur. But the opening quickly began throwing fragments of glowing rock into the air. By night, the new vent was visible as a fountain of fire. Material fell around it, and a cone began to build. A volcano was not awakening from an old summit. It was constructing its summit in front of witnesses. The growth was astonishing on a human timescale. During its first days, the cone rose rapidly as cinders and bombs accumulated around the vent. lava advanced across fields. Scientists arrived with notebooks, cameras, and instruments, able to observe the life of a monogenetic volcano almost from birth. The word monogenetic means that the volcano is built during a single eruptive episode rather than repeatedly reusing the same central edifice over long spans. Pericuden continued erupting for about 9 years. Its behavior changed over time. Explosive bursts built the cone, while lava flows spread outward and buried farmland. The nearby villages of Pericuden and San Juan Parangaricutero were abandoned as lava approached. A church tower and part of a stone facade remained standing above the dark rock, becoming one of the most haunting images of the eruption. Human architecture surrounded by a landscape younger than the people who had built it. No part of this was gentle for the communities whose homes and land were lost. Yet the eruption gave volcanologists something rare. Most volcanoes are encountered midway through stories that began thousands of years earlier. At Pericuden, observers could see how a vent opened, how loose fragments accumulated into a cone, how lava found channels, how wind carried ash, and how an eruption changed from one phase to another. It also revealed how quickly maps can become outdated. A field became a vent. Paths disappeared beneath lava. A cone rose where no cone had been marked. Valleys redirected flows. Older hills shaped the new landscape, and communities had to reimagine where it was possible to live. Geology, which often seems to belong to deep time, entered the calendar of ordinary lives. When the eruption ended in 1952, the volcano became quiet. The cone did not vanish. Weather began its slower work. Rain cut small channels into ash and cinder. Plants returned to some surfaces. Lava cooled from red to black and then weathered under sun and storms. Pericuden moved from active process to geological memory, but the transition was not sudden. Heat remained in places, loose material shifted, and the altered land continued to settle into its new form. The story changes the way a volcanic cone can be seen. It is easy to regard a mountain as a permanent object. Pericuden shows the mountain as an event. Layer by layer, fragment by fragment, it rose from a crack in cultivated ground. Its birth was rapid, its active life was brief, and its shape now carries the record of those 9 years. A volcano can be a place, but sometimes it is also a chapter with a visible beginning and end. A caldera is not, by itself, a sign that an enormous eruption is approaching. It is a landform created by collapse, often ancient, sometimes filled by lakes, towns, forests, or geothermal fields. Systems such as Yellowstone, Campi Flegrei, Long Valley, and Toba are studied carefully because their histories are important, not because every small earthquake or rise of the ground means catastrophe. Scientists compare many signals at once: deformation, seismicity, gases, heat, and changes in water. Monitoring is not alarm. It is the patient work of learning what counts as ordinary behavior for a complicated volcanic system. One of the clearest ways to understand a caldera is to visit a place where the collapse has become part of a peaceful landscape. In southern Oregon, Crater Lake fills the deep basin left by the collapse of Mount Mazama. Today, the lake is intensely blue, enclosed by steep walls and forests. Nothing about the still water immediately suggests that the missing summit once stood high above it. Roughly 7,700 years ago, Mount Mazama produced a powerful sequence of eruptions. Pumice and ash spread across a wide region. Pyroclastic flows moved down the mountain's sides. As magma was removed from beneath the summit, the unsupported upper part of the volcano collapsed inward. The result was not a crater blasted out like a simple bowl. It was a large collapsed structure created because the foundation beneath the mountain had changed. Later, rain and snow began filling the basin. There is no large river flowing into or out of Crater Lake. Water arrives mainly from precipitation and leaves through evaporation and seepage. Over time, the caldera became a lake, and later eruptions built volcanic features within it, including Wizard Island. The system did not move from volcano to non-volcano in one step. Collapse, cooling, water, renewed eruptions, erosion, and ecology continued the story. The setting is a reminder that geological violence does not remain visually violent forever. Ash can support forests. A collapsed summit can hold water. Cliffs created in catastrophe can become nesting places and landmarks. The calm surface of a caldera lake is not a denial of what happened. It is what happened next. This is why a caldera should be understood through history rather than appearance alone. Some are occupied by lakes. Some contain towns, farms, hot springs, or new volcanic cones. Some have been quiet longer than written history. Their shape tells us that a large volume changed underground, but their present condition must be read from present evidence. The old collapse explains the landscape. Monitoring explains the current state. Magma chambers are also not usually giant open caverns of liquid. Many are better imagined as crystal-rich mush, partly molten zones where melt exists between crystals in complex networks. This matters because a volcano may have heat, and some melt beneath it without being ready to erupt. Eruption requires enough mobile magma, enough pressure, and pathways to the surface. A warm system is not automatically an erupting system. Hawaii tells a different volcanic story because the islands are not arranged along a plate boundary. The Pacific Plate moves across a region of persistent melting beneath it, leaving a chain of volcanoes and seamounts that becomes older toward the northwest. The active end of the chain lies around the island of Hawaii, while older islands have traveled away, eroded, subsided, and in some cases become low atolls or flat-topped seamounts beneath the sea. Measured from its base on the ocean floor, Mauna Kea rises farther than Mount Everest rises above sea level. Mauna Loa is among the largest volcanoes on Earth by volume, built from layer after layer of fluid basalt. Yet the youngest member of the Hawaiian chain is still underwater. Kemawakana formerly widely known as Leahy Seamount, rises from the seafloor south of Hawaii Island but remains nearly a kilometer below the surface. It may eventually emerge if eruptions continue to build it, though that could take many tens of thousands of years, perhaps much longer. An island can begin as a mountain no one standing at the surface can see. The chain turns geography into a clock. By dating lava on islands and seamounts, scientists can trace the motion of the Pacific Plate across millions of years. A row of tropical islands becomes a record of direction and speed. Beaches, cliffs, reefs, and rainforests occupy the brief exposed stage of volcanoes whose full lives begin and end beneath the ocean. Volcanic forecasting is possible in a way earthquake prediction usually is not because magma often announces movement. Rising magma fractures rock, causing earthquake swarms. It pushes ground upward or outward, producing deformation. It releases gases. It changes heat flow and sometimes alters the chemistry of springs and fumaroles. No signal is perfect alone, but together they can show whether a volcano is becoming restless. Seismometers near volcanoes listen for different kinds of earthquakes. Volcano-tectonic quakes come from brittle rock cracking. Long-period events can suggest fluid movement. Tremor can indicate sustained movement of magma or gas. The patterns are complex, and each volcano has its own personality. Monitoring works best when scientists know the background behavior of a volcano before a crisis begins. GPS stations and satellite radar can measure ground movement with astonishing precision. A volcano may inflate as magma enters a shallow storage region, then deflate as magma drains or pressure changes. This breathing can occur without eruption, but it is valuable information. The ground becomes a slow instrument. Its surface records pressure changes below. Gas monitoring is another window. Sulfur dioxide, carbon dioxide, hydrogen sulfide, and water vapor can reveal magma rising or degassing. Carbon dioxide can escape from magma at greater depth than sulfur dioxide, so changes in gas ratios can matter. But gas can also be filtered through water and rock. Interpretation requires care. A volcano does not speak in one language. It speaks in overlapping signals. Thermal cameras and satellites can detect heat from new lava, hot cracks, crater lakes, and fumaroles. Satellites can also track ash clouds, sulfur dioxide plumes, and ground deformation across remote regions. Modern volcanology is both local and orbital. A scientist can stand near a volcano with instruments, and another can watch from space. The mountain is studied from many distances at once. The value of all these instruments becomes clearest when a volcano begins to change. One of the most important examples came from Mount Pinatubo in the Philippines in 1991, when observations gathered from earthquakes, gas, ground changes, and fieldwork had to be turned into decisions while the mountain was moving toward a major eruption. Pinatubo had been quiet in living memory when unrest began in 1991. Small earthquakes multiplied beneath the volcano. Steam explosions opened vents. Sulfur dioxide emissions rose, then changed as magma moved through the system. Scientists from the Philippines and the United States worked under intense uncertainty, trying to decide whether the signals would fade or lead to a major eruption. Warnings and evacuations moved tens of thousands of people away before the largest explosions. The eruption was still devastating. Ash mixed with rain from a passing typhoon, roofs collapsed, valleys filled with volcanic debris, and lahars continued to reshape the region for years. But the number of lives saved made Pinatubo one of the clearest demonstrations that careful monitoring can change the human outcome of a natural event. The volcano could not be stopped. The disaster could be reduced. Mount St. Helens in 1980 offered a different lesson. A volcano may not release its energy straight upward, and the shape of the mountain can become part of the eruption. During the spring, magma pushed into the north side, creating a bulge that grew day after day. On May 18th, an earthquake triggered the collapse of that weakened flank. The landslide removed pressure from the shallow magma system so abruptly that a blast escaped sideways across the landscape. The event changed how scientists thought about unstable flanks, landslides, and eruptions directed not toward the sky, but across valleys and forests. Forests were flattened over a broad area. A vertical eruption column later rose high into the atmosphere, and ash traveled across much of the United States. Yet the eruption also revealed how uneven disturbance can be. Some places were scoured almost bare. Others retained patches of snow, roots, seeds, burrowing animals, or fallen trees that sheltered new growth. In the decades that followed, ecologists watched life return not as a smooth wave, but as a mosaic. Recovery followed countless small pathways. Far earlier, Vesuvius left one of the rare places where history, archaeology, and volcanology meet in the same deposit. In the year 79, Pliny the Younger watched from across the Bay of Naples as a dark cloud rose above the volcano and broadened at the top like a Mediterranean pine. His uncle, Pliny the Elder, sailed toward the danger, partly from scientific curiosity and partly to help people escape. He did not return. The eruption buried Roman towns, but it also preserved an eyewitness description detailed enough to become part of modern scientific language. Pompeii was buried mainly beneath pumice and ash, while Herculaneum was overwhelmed by hot pyroclastic currents and later volcanic deposits. The burial preserved streets, rooms, wall paintings, tools, food, graffiti, and the shapes of ordinary lives interrupted. Centuries later, archaeology recovered a city, and volcanology recovered the sequence of an eruption. A letter written by one witness eventually gave its name to an entire style of explosive eruption, Plinian. Tambora in 1815 widened the scale once again. The summit collapsed into a caldera, nearby communities were devastated, and sulfur injected high into the atmosphere spread far beyond Indonesia. The following year became known in parts of Europe and North America as the year without a summer. Cold, rain, and unusual weather damaged harvests and pushed food prices upward. One mountain had altered sunlight enough to join distant weather, hunger, migration, and culture into the same geological story. At Lake Geneva, persistent bad weather kept a small group of writers indoors. Among them was Mary Godwin, soon to become Mary Shelley. A challenge to invent ghost stories helped produce Frankenstein. The novel was not caused by Tambora in any simple sense, but the chain is still remarkable. Magma arose beneath an Indonesian island. Sulfur altered sunlight. Weather darkened a European summer, and one of literature's most enduring stories took shape beside a cold lake. Geology had entered culture from the other side of the world. Another Indonesian volcano reveals a different kind of continuation. Krakatau stood in the Sunda Strait between Java and Sumatra, where one tectonic plate descends beneath another. Its famous eruption in 1883 destroyed much of the old volcanic island and generated tsunamis that struck surrounding coasts. The explosion was heard across an extraordinary distance, and pressure waves traveled through the atmosphere around the globe. Yet the most revealing part of the story came later. The empty-looking sea above the collapsed structure did not remain empty. Underwater eruptions resumed. In 1927, observers saw new activity break the surface. A small cone repeatedly appeared, was attacked by waves, and sometimes disappeared again. Eventually, it grew more persistently. It was named Anak Krakatau, the child of Krakatau. The name captures something important about volcanoes. They are not always single mountains with a single lifetime. A volcanic system can destroy an edifice and then begin constructing another within the old collapse. Eruption builds material above the sea. Waves remove it. New lava strengthens the island. Rain cuts gullies. Plants arrive. Then another eruption changes the shape again. Anak Krakatau grew through much of the 20th and early 21st centuries, but growth did not mean stability. Volcanic islands can be steep, layered, fractured, and partly supported by material below sea level. In 2018, a section of Anak Krakatau's flank collapsed during an eruption, displacing water and producing a destructive tsunami in the Sunda Strait. The event was a reminder that not every volcanic tsunami begins with a large earthquake. The movement of the volcano itself can move the sea. After the collapse, the island was lower and reshaped, but activity continued. The child of Krakatau had entered another stage rather than reaching a final form. Its story is one of construction, collapse, erosion, and rebuilding, all occurring fast enough to be recorded in photographs and satellite images. Across deep time, many volcanic islands follow a similar rhythm more slowly. They emerge, grow, erode, subside, fracture, and sometimes renew themselves through later vents. Some become broad islands with soils and forests. Some are cut into rings of smaller islands around a submerged caldera. Some sink until only coral reefs or flat-topped seamounts preserve the outline of former land. The ocean does not merely surround volcanic islands. It edits them continuously. Flood basalt eruptions belong to a different scale. They are not single cone eruptions, but vast outpourings of basalt over long intervals. The Siberian traps and Deccan traps are famous examples. Such eruptions can release enormous amounts of gas over thousands to millions of years, influencing climate, oceans, and life. The Earth can be gentle in ordinary motion and overwhelming in rare events. Deep time contains both. Volcanic soils can become remarkably fertile after weathering. Fresh volcanic ash and lava are not immediately garden soil, but over time, minerals break down and release nutrients. Many volcanic regions support dense agriculture precisely because old eruptions enrich the ground. This is one reason people live near volcanoes despite risk. The same mountain that threatens can also nourish, supplying soil, water, minerals, and geothermal heat. The deep carbon cycle ties volcanism to climate over immense spans. Carbon dioxide leaves the interior through volcanic degassing. Weathering of silicate rocks removes carbon dioxide from the atmosphere and locks it into carbonates and sediments. Subduction carries some of that carbon back downward. This cycle works slowly, but it has helped Earth maintain liquid water through changes in solar brightness and planetary history. Volcanoes are part of a thermostat too slow for weather, but crucial for climate. Volcanoes also help explain the existence of the atmosphere and oceans. Early Earth released gases from its interior through volcanic outgassing. Water vapor, carbon dioxide, nitrogen, sulfur gases, and other compounds shaped the young atmosphere and surface environment. Some water may also have arrived from impacts and hydrated materials. The exact mixture is studied, but the larger truth is clear. Earth's surface conditions were built through interactions among interior, impact history, atmosphere, and oceans. Earthquakes and volcanoes often share tectonic settings, but they are not the same phenomenon. Many earthquakes happen with no volcano nearby. Many volcanic earthquakes are small and local. At subduction zones, both are common because plates descend, faults lock, magma forms, and the crust is stressed. The Ring of Fire is not a magical ring. It is a broad pattern of plate boundaries around the Pacific, where subduction and plate interactions concentrate geological activity. Japan, Chile, Alaska, Indonesia, New Zealand, the Philippines, and the west coast of the Americas all belong in different ways to this Pacific pattern. Their hazards differ because geometry differs. The angle of subduction, the speed of convergence, the age of the plate, the shape of the coastline, the structure of the crust, and the design of cities. Geology is global, but risk is local. Tsunamis are waves of displacement, not ordinary wind waves. In deep water, they can be low and fast, passing under ships unnoticed. Near shore, slowing water causes the wave to grow, compress, and sometimes arrive as a surge rather than a curling breaker. Earthquakes are the most common cause of major ocean-crossing tsunamis, but landslides, eruptions, and impacts can also displace water. The quiet fact is that warning systems are built from this physics. Tsunami warning centers use seismic data, sea level gauges, deep ocean pressure sensors, and models to estimate whether a dangerous wave has been generated. Far from the earthquake, there may be hours for warnings. Near the origin, there may be only minutes. This is why natural warning signs matter near coasts. Strong shaking, sudden sea retreat, or unusual ocean behavior can be a signal to move inland and upward without waiting for an official message. In the deep ocean, a tsunami may travel as fast as a jet aircraft, while remaining only a modest rise and fall of the water's surface. Its energy is spread through a very long wave. As it reaches shallower water, the lower part of the wave interacts with the seafloor, the wave slows, and its height can increase. The coast does not receive an ordinary breaker enlarged to impossible size. It may receive a fast rising flood, a series of surges, or water rushing inland, and then returning with equal force. The first wave is not always the largest, and the danger may continue for hours. This is why a shoreline that suddenly empties can be deceptive. The retreating sea may expose rocks and seafloor, but it is not an invitation to explore. It can be the trough of a tsunami arriving before the crest. Near the source, the strongest warning may be the earthquake itself, shaking long or strong enough to make standing difficult is a reason to move inland and uphill immediately. One earthquake helped turn these separate clues into a more modern science of hazards. On the morning of November 1st, 1755, Lisbon was one of Europe's great Atlantic cities. It was a religious holiday, and candles burned in homes and churches. Then the ground began to move. The shaking lasted long enough to damage stone buildings across the city, and many people fled toward the open waterfront, away from falling walls. There, the sea behaved strangely. Water withdrew from parts of the harbor, exposing ground that was normally submerged. Then a series of large waves entered the Tagus estuary and swept through low areas. Fires, fed in part by the many candles and damaged buildings, continued after the shaking. The event became not one disaster but a chain: earthquake, tsunami, and fire, each interacting with the shape and habits of the city. Lisbon was not the largest earthquake ever known, and it occurred before seismometers could record its magnitude. Yet its influence reached far beyond Portugal. Shaking was reported across a wide region. Waves crossed the Atlantic and were observed on distant coasts. European thinkers argued about what the event meant, while officials faced the more immediate questions of rescue, rebuilding, and prevention. The response included one of the earliest systematic attempts to collect earthquake information over a broad area. Questions were sent to towns and parishes. How long did the shaking last? In which direction did objects move? What happened to wells and springs? Was the sea disturbed? The answers helped map the event through human observations. Long before digital sensors, a network of witnesses became a scientific instrument. Rebuilding also became part of the lesson. New structures in central Lisbon were designed with internal wooden frameworks intended to flex during shaking. Models were reportedly tested by having troops march around them, creating rhythmic vibration. The method was simple by modern standards, but the idea was profound. A city did not have to choose between stone rigidity and collapse. Buildings could be designed with motion in mind. This is one reason the Lisbon earthquake remains important. It sits at a turning point between interpreting an event only through fear and beginning to investigate it through evidence. People asked where the shaking was strongest, why the sea moved, how fire spread, and how buildings might behave differently next time. The questions did not undo the loss. They transformed part of it into knowledge. Modern hazard science still follows the same chain of reasoning. What moved? How did energy travel? Which ground conditions amplified it? Which structures failed and which survived? Where did water go? How did communication shape the response? An earthquake begins underground, but its human outcome is written through coastlines, soil, construction, timing, and preparation. Lisbon made that wider story impossible to ignore. The ocean floor carries a magnetic memory. As basalt cools at mid-ocean ridges, magnetic minerals align with Earth's magnetic field. Because Earth's magnetic field has reversed many times, the seafloor preserves stripes of normal and reversed magnetization on either side of ridges. These magnetic stripes were crucial evidence for seafloor spreading. The ocean floor is like a slow tape recorder, recording both lava formation and magnetic history. Imagine following one small patch of that basalt from the moment it forms. At first, it is molten rock entering black ocean water along a ridge. Its outer surface chills almost instantly. Inside, it cools more slowly. Tiny magnetic minerals settle into alignment with the field that surrounds Earth at that moment, and then the rock hardens around them. The patch has acquired a direction, a magnetic memory too weak for a hand to feel, but clear enough for instruments to measure. Year after year, new magma rises behind it. The patch is carried away from the ridge by motion so slow that no person could watch it happen. Sediment begins to collect on top. Dust falls through the ocean. Shells and microscopic remains settle. Hydrothermal circulation cools the crust and changes some of its minerals. The once new seafloor becomes older, colder, denser, and more heavily covered. During its journey, Earth's magnetic field may reverse. Basalt formed later at the ridge records the opposite orientation. Then the field reverses again, and another band is added. Because new crust is created on both sides of the ridge, the bands appear in matching sequences, like the two halves of a pattern opening away from a central seam. When marine geophysicists towed magnetometers across the ocean after the Second World War, they found these unexpected stripes repeating over enormous distances. At first, the pattern looked almost decorative, a set of invisible zebra bands beneath the sea. But it contained a history. In the early 1960s, researchers connected the stripes to magnetic reversals and seafloor spreading. The ocean crust was not merely recording the field. It was revealing its own movement. Each stripe had formed at the ridge and then traveled outward, carrying a timestamp written in magnetism. Our small patch of basalt may continue for tens of millions of years. Eventually, it approaches a trench. The seafloor ahead bends downward. Earthquakes outline a descending plane beneath an island arc or continent. Sediment is scraped away in some places and carried downward in others. The patch tilts, fractures, and begins to sink into the mantle. There, its journey becomes harder to follow. Minerals transform under pressure. Water locked inside them is released. Some ingredients may help generate magma above the descending slab. That magma may rise and erupt through a volcanic arc, creating new rock at the surface. A piece of ocean floor born in darkness may therefore return indirectly as ash on a mountain, crystals in granite, or lava cooling beneath a different sky. The cycle is not a perfect circle, and no individual atom is guaranteed a simple route. Some material remains in the mantle for immense periods. Some is mixed, transformed, or carried deeper. But the overall movement is clear. The ocean floor is created, travels, ages, and returns. When geologists speak of plate tectonics, they are describing not only moving continents, but countless journeys like this one, each too slow to watch and large enough to remake the world. Continents are more buoyant than oceanic crust because they are thicker and less dense. They resist subduction in a way oceanic lithosphere does not. This is why continents can preserve rocks billions of years old, while most ocean floor is much younger. Continents are archives. They keep ancient mountain roots, old cratons, fossil shorelines, and mineral records of vanished oceans. Volcanic and seismic processes shape them, but they also endure. Mountain building often involves collisions. When ocean basins close and continents meet, neither side easily sinks. Crust thickens, folds, faults, and rises. The Himalayas are the result of India colliding with Eurasia, a process still continuing. Earthquakes in such regions come from the ongoing adjustment of enormous crustal masses. Mountains are not finished sculptures. They are active negotiations between uplift and erosion. Rifting is the opposite kind of beginning. A continent stretches, fractures, and thins. Valleys form. Volcanoes may appear. If rifting continues long enough, seawater may enter and a new ocean basin can open. The Red Sea and East African Rift reveal parts of this story. Continental breakup is not instant. It is a long weakening, a slow invitation for an ocean that may or may not fully arrive. Hotspots add another pattern to the map. A plate can move over a relatively persistent region of mantle melting, producing a chain of volcanoes that grows older away from the active center. Hawaii is the classic example. The islands and seamounts record Pacific plate motion across a deep melting anomaly. A map of volcano ages becomes a track of plate movement. Not all hotspots are simple, and not all volcanic chains have one explanation. Mantle plumes, lithospheric cracks, plate stresses, and inherited structures can interact. Earth science often begins with a clean diagram and then discovers that nature is more complex. This complexity is not failure. It is the reason the subject remains alive. Each volcano is a local expression of general rules and local history. Geysers and hot springs show the softer side of volcanic heat. Water sinks into the ground, is heated by hot rock or magma-related systems, and returns to the surface carrying minerals and heat. In geysers, underground plumbing allows pressure to build until water flashes into steam and erupts. The result is an eruption made not of magma, but of water and heat. Even hydrothermal systems have rhythms. Hydrothermal vents on the seafloor connect volcanic heat to life. At mid-ocean ridges and other settings, seawater circulates through hot rock, dissolves minerals, and emerges as chemical-rich fluid. Around some vents, ecosystems thrive without sunlight, using chemical energy. This is not the origin of life by itself, but it shows that Earth's internal heat can support living systems indirectly. The deep Earth and biology are not separate stories. Earth's magnetic field is another gift of the moving interior. The liquid outer core convects, and Earth's rotation helps organize the motion into a dynamo. The magnetic field shields the planet from some charged particles from the sun and helps shape the space environment around Earth. The same planet that moves plates and produces volcanoes also maintains an invisible magnetic envelope. Deep motion has surface consequences. The magnetic field also reverses irregularly over geological time. North and south magnetic poles have swapped many times. These reversals are recorded in volcanic rocks and ocean crust. They do not happen on a human schedule, and they are not disasters in the cinematic sense. They are part of the natural behavior of the geodynamo. Rock remembers them patiently. Seismic tomography is like a medical scan of the planet. By measuring how waves from many earthquakes travel through Earth, scientists build images of faster and slower regions inside the mantle. Cold subducted slabs often appear as faster regions. Hot rising material can appear as slower regions. The pictures are not photographs, but they are powerful reconstructions. The deep mantle becomes a landscape of temperature and motion. The deepest mantle may contain large provinces with different seismic properties, sometimes called large low shear velocity provinces. Their nature is still debated. They may be hotter, compositionally different, or both. Some mantle plumes may rise from their edges. This is part of the frontier of deep Earth science. Even the broad outlines of the planet are known, while details remain open enough to invite new instruments and ideas. The surface record can also reveal past earthquakes. Paleoseismology studies old fault ruptures through trenches, offset layers, buried soils, and disturbed sediments. A fault that has not ruptured in written history may have done so many times before writing existed. By reading layers across a fault, scientists can estimate past events and recurrence patterns. The ground becomes an archive of shaking. Volcanoes also leave archives. Ash layers and lake sediments, ice cores, peat, ocean cores, and archaeological sites can be matched chemically to particular eruptions. This field, tephrochronology, lets scientists connect records across regions. A thin ash layer may mark the same year in many places, becoming a timeline in the Earth. A single eruption can become a page marker for climate, archaeology, and geology. Ice cores preserve sulfate from major eruptions, allowing scientists to estimate the timing and atmospheric effect of ancient volcanic events. Tree rings can show years of unusual cold. Historical records can describe dim suns, failed harvests, or strange skies. The story of an eruption can therefore be reconstructed from ice, wood, writing, and ash. Earth history is often assembled from quiet fragments. A volcanic ash layer can be thinner than a finger and still connect places separated by continents. Its glass shards carry a chemical signature, a mixture distinctive enough to match the ash in a lake bed with ash in an archaeological trench or an ice core. Once the match is made, distant records share the same time marker. A change in pollen, a human tool, a climate shift, and a volcanic deposit can all be placed on the same page of history. This is one reason a volcano can remain scientifically present long after its cone has eroded or disappeared. The eruption survives in sediments, in microscopic glass, in sulfate trapped in snow, in damaged tree rings, and in stories written beneath strange skies. The event is over, but its traces continue to speak in several languages at once. The Earth also has a low hum. Even when no earthquake is happening, sensitive instruments record continuous vibrations from oceans, weather, human activity, and the planet's own normal modes. Huge earthquakes can make Earth ring like a bell at frequencies far below hearing. The phrase is poetic, but the measurement is real. The planet has tones too low for ears, carried through rock. Human activity has become part of the seismic background. Traffic, factories, trains, construction, and machinery add small vibrations to seismometers. During periods when human activity suddenly decreases, seismologists can sometimes detect weaker natural signals more clearly. Even our quiet or noise becomes visible to instruments. The ground records both geology and civilization. Volcanic lightning can occur in ash plumes when particles collide and separate electrical charges. The sight is dramatic, but the principle is familiar: charged particles, turbulence, and discharge. Eruptions create weather-like systems inside ash clouds, with ice, ash, water, and electric charge interacting. A volcano can briefly make its own storm. Volcanic gases affect atmosphere and climate in different ways. Water vapor is abundant, but usually returns quickly through the water cycle. Carbon dioxide matters over longer climate timescales. Sulfur dioxide can form sulfate aerosols that reflect sunlight and temporarily cool the surface after large explosive eruptions. The effect depends on eruption size, latitude, season, and how high material reaches. Not every eruption changes climate, but some do. Ash clouds matter to aviation because fine particles can melt inside jet engines and then solidify in damaging ways. This is why volcanic ash advisories are so important. A cloud that looks like dust from a distance can be a serious hazard to aircraft. Modern monitoring with satellites, weather models, and volcano observatories helps aircraft avoid dangerous ash. Science becomes practical through warning maps. Volcanic islands are born, eroded, and sometimes erased. Surtsey, formed near Iceland in the 1960s, became a natural laboratory for studying colonization by plants, birds, insects, and microbes. A new island is not only new rock. It is an experiment in how life arrives, how soil begins, how weather shapes fresh lava and ash. Volcanoes create surfaces on which ecology can start over. Surtsey's story began before anyone could see land. In November 1963, the crew of a fishing vessel south of Iceland noticed smoke rising from the sea. At first, it might have looked like a ship fire. Then dark columns of ash and steam climbed higher, and explosions broke through the surface. An eruption was happening on the seafloor, where seawater met rising magma. The first material was fragile. Explosive contact between water and magma shattered rock into ash, building a low island that waves immediately tried to remove. Each storm attacked the loose deposits. For a time, creation and erosion competed almost hour by hour. The eruption had to build fast enough to keep part of the island above water. As the vent became better protected from the sea, the eruption style changed. Lava flows spread across the young surface. Unlike loose ash, solid lava resisted waves more effectively and formed a protective cap. By the time activity ended in 1967, Surtsey had become a lasting island, although not an unchanging one. The Atlantic continued cutting cliffs, moving beaches, and carrying material away. Scientists recognized an unusual opportunity. Most islands are already biologically complicated by the time they are studied. Surtsey began as sterilized volcanic material, isolated enough that the arrival of life could be watched in sequence. Access was restricted so that visitors would not accidentally carry seeds, soil, or organisms that could confuse the natural experiment. Life did not wait long. Microbes arrived. Seeds traveled by wind and water. Birds landed and left droppings rich in nutrients. Insects were carried by air currents, floating debris, and visiting animals. Some early plants failed. Others survived and spread. Bird colonies later accelerated soil formation, turning bare surfaces into patches where more species could establish. The island showed that colonization is not a tidy parade in which one species always prepares the way for the next. Arrival is partly chance. Survival depends on salt, wind, exposure, available nutrients, and the exact surface on which an organism lands. A seed may reach the island and die. Another may arrive inside driftwood, beside a sheltered rock, or near a bird colony and find the conditions it needs. At the same time, Surtsey kept shrinking. This did not mean the island had failed. Erosion is part of the life of every volcanic island. Waves cut into tuff. Cliffs collapsed. Sand and gravel moved around the shore. The durable lava core remained while softer material was lost. By measuring these changes, scientists could watch geology and biology unfold together. Rock creating habitat, ocean removing it, and life using the temporary spaces between. Surtsey is therefore more than a young island. It is a compressed version of a much longer planetary story. Heat from inside Earth created rock. Water reshaped it. Air and ocean carried life. Birds changed the soil. Plants held some surfaces together. Storms continued to erase the edges. In one small place, the deep earth, the sea, the atmosphere, and living organisms began negotiating a landscape from the beginning. Seamounts are underwater volcanoes, many never reaching the surface. Some become islands temporarily, then erode and sink into geos, flat-topped underwater mountains. The ocean hides countless volcanic forms. A map of the seafloor reveals chains, ridges, plateaus, cones, and scars. The surface of the sea looks smooth, but below it the planet has architecture. Earthquakes can lift or lower coastlines in moments. During great subduction earthquakes, locked plates release strain, and parts of the coast may rise while others subside. Coral reefs, marshes, drowned forests, and uplifted marine terraces can preserve these changes. A coastline is not fixed. It is a moving boundary between ocean, land, and plate motion. Some earthquakes happen within plates, far from active boundaries. Intraplate earthquakes are less common, but can be important because regions away from plate boundaries may be less prepared. Old rifts, ancient faults, and stress transmitted through a plate can produce earthquakes long after a tectonic feature formed. The crust remembers weaknesses. A very old structure can still influence modern shaking. The New Madrid earthquakes showed that the interior of a continent can still move. Their effects traveled far because Eastern North America transmits seismic waves efficiently through old, cold crust. An earthquake of the same magnitude can be felt across different distances depending on regional geology. The continent itself shapes the experience of shaking. During the winter of 1811 and 1812, a sequence of powerful earthquakes struck near New Madrid along the Mississippi River. Written accounts describe cracking ground, landslides along riverbanks, trees thrown down, and waves on the river that made the current appear to reverse in places. The shaking was felt across an enormous area, far beyond what many people expect from an earthquake in the interior of a continent. The reason lies partly in the crust itself. Old, Cold continental rock in eastern North America transmits seismic energy efficiently, allowing shaking to travel farther than it often does through the more fractured crust of the western United States. The New Madrid zone follows an ancient failed rift, a place where the continent began to pull apart hundreds of millions of years ago and then stopped. The rift did not become an ocean, but it left weaknesses behind. Geological plans can be abandoned without being entirely erased. The San Andreas Fault is often imagined as a single line, but the plate boundary in California is a network of faults. Stress is distributed across the San Andreas, Hayward, Calaveras, San Jacinto, and many others. Some creep slowly, some lock, some rupture in damaging earthquakes. A plate boundary can be a zone, not just a cut. Maps simplify, while the crust contains many strands. Earthquake preparedness is practical calm. Secure heavy furniture. Know safe places. Keep emergency supplies. Learn local guidance. Build and retrofit well. These steps do not predict earthquakes, and they do not remove hazard, but they turn knowledge into readiness. Calm is not denial. Calm is preparation without panic. Volcano preparedness is also local. Living near a volcano may require evacuation routes, ashfall plans, masks, water protection, roof load awareness, and attention to official observatory updates. Different volcanoes have different hazards: lava, ash, gas, lahars, pyroclastic currents, landslides, or tsunamis. Knowing the particular volcano matters more than knowing the word volcano in general. The relationship between fear and knowledge changes as the science becomes clearer. A volcano is not a monster. It is a system. A fault is not a punishment. It is a surface where stress is stored and released. A tsunami is not a wave with intention. It is displaced water obeying physics. Understanding does not make hazards harmless, but it removes some of the darkness around them. The Earth has always changed. Continents that seem permanent have assembled and broken apart many times. Supercontinents formed and separated: Nuna, Rodinia, Pangaea, and perhaps others with names still debated. Oceans opened and closed. Mountain belts rose and eroded away. Volcanoes built provinces now worn into quiet hills. Today's map is only one frame in a long film. Pangaea is recent in deep time terms, existing when many now separate continents were joined. Its breakup helped open the Atlantic Ocean. The Mid-Atlantic Ridge is part of that continuing separation. South America and Africa still carry the memory of fitting together, not only in shape but in matching rocks, fossils, and structures. Wegener's idea was once mocked, but the continents were patient witnesses. The acceptance of plate tectonics was one of the great scientific revolutions of the 20th century. It united continental drift, seafloor spreading, earthquakes, volcanoes, mountain building, and ocean trenches into one framework. Before it, many facts stood separately. After it, the planet became coherent. This is one of the pleasures of science. Scattered observations can suddenly become one story. Ocean trenches mark places where plates descend. They are among the deepest parts of the ocean, formed by bending lithosphere and subduction. The Mariana Trench is the most famous, but trenches ring much of the Pacific. Their darkness and depth correspond to some of Earth's strongest tectonic forces. The deepest ocean is linked to the deepest recycling of crust. Arc volcanoes above subduction zones often erupt andesite or dacite, compositions richer in silica than basalt. These magmas can be sticky and gas-rich, creating explosive potential. The word andesite comes from the Andes, one of the great volcanic arcs. The Andes exist because an oceanic plate is descending beneath South America. A mountain range can therefore be read as a sign of a plate disappearing below it. The Andes also show the link between volcanism and uplift. Subduction produces magma, but compression and crustal thickening build topography. Volcanoes punctuate the mountain belt, while faults and folds raise and deform the crust. Snow, desert, volcano, and earthquake all belong to one tectonic setting. Landscapes are mixtures of processes. In island arcs, one oceanic plate descends beneath another, creating curved chains of volcanic islands. Japan, the Aleutians, the Marianas, and many islands of Indonesia are related to this kind of setting. The curve of an island arc reflects the geometry of a spherical planet and a descending slab. The shape of a coastline can carry information about deep structures. Back arc basins can open behind volcanic arcs when the overriding plate stretches. This shows that subduction is not only compression. The flow of mantle and the retreat of slabs can create extension too. Tectonics resists simple labels. One boundary can produce trenches, volcanoes, earthquakes, mountains, and basins depending on geometry and time. Earthquake depth matters. Shallow earthquakes often produce stronger surface shaking because the energy starts closer to people and buildings. Deep earthquakes may be felt widely, but often with less damaging intensity near the surface. Subduction zones produce earthquakes across a wide range of depths as the descending plate bends and sinks. A map of earthquake depth can reveal the angle of a slab. The Wadati-Benioff zone is the inclined zone of earthquakes within a subducting slab. It descends from the trench into the mantle, tracing the plate's path downward. This pattern was another key clue for plate tectonics. Earthquakes are not scattered randomly under arcs. They form dipping planes. The geometry of seismicity draws the hidden plate. Seismic waves include body waves, which pass through Earth, and surface waves, which travel along the surface. Surface waves often cause much of the damaging shaking in large earthquakes because their motion can be large and sustained. Love waves move the ground side to side. Rayleigh waves roll the ground like ocean swell. The names are scientific, but the motions are physical and real. But the size and type of a wave are only the beginning. Every structure has natural periods at which it tends to sway. Short, stiff buildings respond more strongly to some frequencies, while taller, more flexible buildings respond to others. If incoming waves repeatedly push near one of those natural rhythms, motion can build through resonance. This is why earthquake engineering studies not only how hard the ground moves, but how quickly it moves back and forth. Sediment-filled basins can add another layer. Waves may slow, reflect, and become trapped between basin edges and deeper bedrock, lengthening the shaking. The city above can seem to sit on a geological bowl that continues ringing after nearby rock has quieted. Two buildings at the same distance from a fault may therefore face very different motion because their foundations, heights, and surrounding ground respond to different parts of the seismic signal. Some earthquake hazards come after shaking. Landslides can occur on steep slopes. Fires can start from broken lines. Dams, bridges, and roads can be affected. Liquefaction can damage foundations and buried utilities. Tsunamis may follow offshore ruptures. A seismic event is therefore not only the rupture itself, but a chain of consequences shaped by the built and natural environment. Volcanic hazards also come in chains. An eruption can melt snow, triggering lahars. Ash can block sunlight locally, contaminate water, and affect agriculture. Gas can collect in low areas. Lava can start fires. Heavy ash can collapse weak roofs when wet. Understanding the chain helps communities prepare. The eruption is the beginning of a hazard story, not always the whole of it. Volcanoes can also collapse without a major magmatic eruption. Flank collapses and landslides can reshape mountains and, if they enter water, generate waves. The Hawaiian Islands contain enormous submarine landslide deposits, evidence of past flank failures. The sides of volcanoes are built by layers and intrusions, sometimes unstable over long time. Gravity is always present. Crater lakes can be beautiful and hazardous. Some collect acidic water. Some can release gas. Some can overflow or contribute to lahars. Lake Nyos in Cameroon, though not a typical eruptive event, tragically showed how volcanic carbon dioxide stored in deep lake water can be released. The lesson is that volcanic systems include gases, water, and landscapes as well as lava. Geothermal energy uses Earth's heat more gently. In volcanic and tectonically active regions, hot water and steam can generate electricity or heat buildings. Iceland, New Zealand, parts of the western United States, and other regions use geothermal resources. This is another way the restless Earth supports human life. Heat that can erupt can also warm homes when handled carefully. The deepest drilled holes on Earth reach only a small fraction of the way through the crust. The Kola super-deep borehole reached about 12 kilometers, an impressive distance for engineering, but tiny compared with Earth's radius. Most of what is known about the deep Earth comes not from direct sampling, but from waves, gravity, magnetism, heat flow, and rocks brought upward by tectonic and volcanic processes. Diamonds sometimes carry tiny inclusions from deep within the mantle, bringing clues from depths humans cannot visit. Some volcanic eruptions, such as kimberlite eruptions in the distant past, carried diamonds upward rapidly enough for them to survive. A gemstone can be a geological messenger, not only a decoration. It may carry a mineral memory from deep pressure. Xenoliths are pieces of rock carried upward by magma from deeper levels. A lava flow may contain fragments of mantle or lower crust, allowing scientists to examine materials otherwise unreachable. These fragments are like letters from below, delivered by eruption. The volcano does not only bring melt, it can bring samples of the hidden Earth. Volcanic rocks record time through radioactive isotopes. Minerals contain unstable atoms that decay at known rates, allowing ages to be measured. This dating helps reconstruct eruption histories, plate motions, and volcanic cycles. A black lava rock on a hillside may look timeless, but its minerals contain clocks. Geology often turns stone into time. Earthquakes also reveal time through recurrence. A fault may rupture every few centuries on average, but not on a schedule like a clock. Intervals vary. Stress transfer from one earthquake can slightly increase or decrease stress on nearby faults. Fluids can affect fault strength. Friction evolves. This complexity is why deterministic prediction remains out of reach. The Earth is lawful, but not simple. The phrase earthquake weather is a myth. Earthquakes are controlled by processes kilometers below the surface, not by ordinary clouds, heat, or wind. Very small stress changes from tides, reservoirs, or fluids can matter in particular circumstances, but daily weather does not predict damaging earthquakes. Myths often arise because people look for patterns after frightening events. Science answers by testing patterns carefully. Animals may behave strangely before earthquakes, but this has not become a reliable prediction method. Animals respond to many things: sounds, smells, vibrations, weather, human behavior. After an earthquake, unusual behavior is remembered. Ordinary days are forgotten. Reliable prediction requires a signal that works repeatedly, clearly, and ahead of time. That standard has not been met. Volcano myths are different but related. A volcano may steam, smell of sulfur, shake, or change shape, and these can be meaningful signs. But the meaning depends on context and instruments. Steam may reflect hydrothermal activity, not rising magma. Earthquakes may happen without eruption. Gas may change for several reasons. Volcanology succeeds by combining signs rather than trusting one dramatic clue. The beauty of hazard science is that it serves life. Maps, building codes, evacuation plans, ash advisories, monitoring stations, and public education are all forms of care. They translate deep Earth processes into decisions at the surface. A seismogram may seem technical, but behind it is a wish to understand enough to protect people. The quiet science of volcanoes and earthquakes is therefore not only about power. It is about relationship. Humans live on a planet that moves. We cannot freeze it. We can learn its patterns, respect its histories, build with humility, and listen through instruments. The goal is not to conquer geology, but to belong more intelligently to the Earth. Even the word disaster needs care. A natural process becomes a disaster when it intersects with vulnerable people, buildings, and systems. The earthquake is natural. The vulnerability is partly social. Strong construction, fair planning, warning systems, and prepared communities can turn the same physical event into a very different human outcome. Geology sets hazards. Societies shape risk. Volcano observatories are among the most important quiet institutions in active regions. Teams collect seismic data, gas measurements, deformation maps, field observations, and satellite images. They speak with civil authorities and communities. Much of their work is uneventful, which is exactly the point. Good monitoring is patient. It watches long before the dramatic day. Seismic networks do the same across fault zones. They record tiny earthquakes, locate ruptures, refine hazard maps, and help build early warning systems. A small event that no person feels may still matter to science. It becomes one dot in a larger pattern. Over years, those dots reveal active structures, stress changes, and the hidden texture of a region. The Earth's activity is not evenly distributed, but no place is completely outside geology. Some places have frequent earthquakes, others have rare ones. Some volcanoes erupt often, others sleep for centuries. Some mountains are young and rising, others are old and worn down. Even quiet landscapes are part of deep history. A flat plain may hide buried faults, old lava, ancient seas, or eroded mountains. Weather and erosion are the partners of tectonics. Tectonics raises mountains, erosion wears them down. Volcanoes build cones, rain cuts valleys. Earthquakes uplift land, rivers adjust their courses. The surface we see is not made by one process, but by competition and cooperation among many. Rock rises, breaks, dissolves, settles, and begins again. Sedimentary basins collect the debris of mountains and volcanoes. Ash becomes clay. Lava becomes soil and sediment. Earthquake-triggered landslides send material into rivers. Subduction zones create basins that fill with sand and mud from eroding arcs. The products of violent events can become quiet layers on the seafloor, waiting to be buried, folded, uplifted, and read by future geologists. In deep time, no landscape keeps one identity. A volcano erodes into a hill. A seabed rises into a mountain. A mountain wears down into sand. Sand becomes sandstone. Sandstone is buried, heated, deformed, and perhaps melted. Rock is not a final state. It is a phase in a cycle. Volcanoes and earthquakes are dramatic signs of that cycle. But the cycle continues even in silence. The rock cycle is not separate from plate tectonics. Igneous rocks form from cooling melt. Sedimentary rocks form from fragments or precipitated minerals. Metamorphic rocks form when heat, pressure, and fluids transform older rocks without fully melting them. Subduction carries rocks downward. Uplift brings them back. Erosion exposes them. Magma remakes them. The surface and interior exchange material through time. Metamorphism is one of the quieter, deep processes. Rock can change mineral content and texture while remaining solid. Limestone can become marble. Shale can become slate, schist, or gneiss. Basalt can become blue schist or eclogite under subduction conditions. These transformations record pressure, temperature, and fluids. They show that Earth changes not only by breaking and melting, but by slow rearrangement inside solid rock. Fluids matter deeply in geology. Water and pores can weaken faults by changing pressure. water and minerals can help trigger melting in subduction zones. Hydrothermal fluids can deposit metals and alter rocks. Steam can power geysers. Groundwater can interact with ash and slopes to form lahars. The earth beneath us is not dry machinery. It is often a world of rock, heat, and moving fluids. This is why volcanoes can be connected to or deposits. Hydrothermal fluids moving through volcanic and magmatic systems can carry metals, then deposit them as conditions change. Copper, gold, silver, and other resources are often tied to ancient magmatic systems. Human technology depends in part on deep geological processes. The devices used to study Earth may contain materials made available by Earth's own heat. Earthquake faults can also guide fluids, sometimes acting as pathways and sometimes as barriers. Mineral veins can form when fluids move through fractures and deposit crystals. Some faults become filled with quartz, calcite, or other minerals, sealing and reopening through cycles of stress. A fault zone is not only a mechanical surface, it can be a chemical environment. The connection between earthquakes and volcanoes is most intimate when magma moves. Magma can fracture rock, producing earthquakes. Earthquakes can sometimes alter volcanic or hydrothermal systems by shaking fluids and cracks. But large distant earthquakes usually do not trigger major eruptions. The relationship is subtle, not cinematic. Geological systems can influence each other, but not every shaking event unlocks a volcano. On the rarest scales, volcanism can change much more than a landscape. Large igneous provinces are built by repeated outpourings of basalt over immense areas and long intervals. The Siberian traps erupted around the time of the end Permian mass extinction, the most severe biological crisis known from the fossil record. Gases released directly from magma and from rocks heated by intrusions contributed to rapid warming, ocean acidification, and oxygen loss in the seas. The Deccan traps in India were erupting around the end of the Cretaceous, when an asteroid impact delivered the decisive shock associated with the extinction of the non-avian dinosaurs. Scientists continue to study how prolonged volcanism and sudden impact stress interacted. These events are not ordinary volcano stories enlarged. They belong to a different tempo: many eruptions, vast provinces, repeated gas release, and environmental change accumulating across thousands of years. Deep time contains both kinds of volcanic action. There is the brief lava fountain seen over one night, and there is the province built by eruption after eruption until a region is covered by kilometers of basalt. The same physical process can be intimate enough to warm a spring or extensive enough to alter the history of life. The inside of Earth also keeps its own slow budget of heat. Some heat remains from accretion, when the planet formed from countless impacts and gravitational compression. Some comes from radioactive decay within rocks. Some is released as the core slowly cools and the inner core grows. This heat does not escape in one simple stream. It moves by conduction, convection, magmatism, and hydrothermal circulation. The planet is cooling, but so slowly that its internal warmth still drives enormous surface consequences. Mantle convection is easy to draw and difficult to imagine. Diagrams show neat arrows rising and sinking, but the real mantle is a complex, three-dimensional, slowly deforming shell. Cold slabs sink from subduction zones. Hot regions rise in broad upwellings or narrower plumes. Chemical differences may persist for long periods. Phase changes occur as minerals adjust to pressure. The mantle is not a pot of boiling soup. It is solid rock participating in a deep and patient circulation. Even minerals change their identity with depth. The atoms may remain the same, yet pressure rearranges them into denser structures, rather as the same pieces might be packed into a tighter pattern. Minerals familiar in the upper mantle transform into high-pressure forms deeper down, and those changes alter density and the speed of seismic waves. A descending slab, therefore, does not simply sink unchanged. Its crystals adjust, its water-bearing minerals break down, and its internal structure evolves as it enters conditions that exist nowhere at the surface. The boundary between crust and mantle is called the moho, named after Andrija Mohorovičić, who recognized a sharp change in seismic wave speeds. This boundary is not visible to the eye in ordinary life, but it marks a major change in rock type. Beneath continents, it lies deeper. Beneath oceans, it lies shallower. A hidden surface inside Earth can be mapped because waves notice it. The core mantle boundary is far deeper and stranger. It is where rocky mantle meets metallic core, a boundary between silicate and iron alloy, between solid rock and liquid metal. Temperatures and pressures there are extreme. Some mantle plumes may rise from near this level. Seismic studies reveal uneven structures, ultra-low velocity zones, and deep complexity. The bottom of the mantle is not a simple floor. It is an active frontier. Earth's rotation is also part of the deep story. The flow of liquid iron in the outer core, shaped by rotation and convection, creates the geodynamo. Without that motion, the magnetic field would fade. The magnetic field is not perfectly steady. It wanders, weakens, strengthens, and reverses over time. The quiet compass needle is connected to churning metal thousands of kilometers below. Although the geodynamo is persistent, it is not perfectly smooth. Magnetic north wanders. The strength of the field changes, and local measurements must be updated as the flow of the outer core slowly reorganizes. A compass appears calm because the change is small from day to day, but even its direction belongs to a moving planet. Cooling lava can preserve those changes. So can clay that was heated in an ancient hearth or kiln. When magnetic minerals cool, they may lock in the field direction of that moment. Archaeomagnetism uses such records to help date old fires, buildings, and volcanic flows. A fragment of burned earth can therefore connect human history to motion in the liquid core thousands of kilometers below. Field reversals are the largest version of this behavior. They do not arrive on a regular schedule, and they do not flip the planet's magnetism in a single night. The transition unfolds over geological time, with the field becoming more complicated before a new polarity is established. Lava flows preserve many such reversals, showing that they are recurring features of the geodynamo rather than signs that the Earth has suddenly become unstable. The oldest continental rocks survive in cratons, stable cores of continents that have endured for billions of years. These ancient regions are thick, buoyant, and resistant. They carry clues about early crust, early atmosphere, early oceans, and early life. Earthquakes can still occur within cratons, but their long-term stability contrasts with the restless margins where plates collide, rift, and subduct. Subduction is not only a recycling process, but a water cycle. Minerals in oceanic crust and sediments carry water downward in bound form. Some water is released at depth and helps generate magma. Some may travel deeper into the mantle. Earth's surface water and deep interior may exchange material over geological time in ways still being studied. The ocean is not entirely disconnected from the mantle below it. Serpentinization is one of the quiet chemical reactions that links rock and water. When water reacts with certain mantle rocks, new minerals form and hydrogen can be produced. This hydrogen can feed chemical reactions and microbial ecosystems in some settings. It also matters for origin of life discussions and hydrothermal systems. A rock reacting with water can become a source of chemical energy. Volcanoes often appear where melting is favored, but melting usually begins as partial melting. Only a portion of the rock melts, and that melt may have a different composition from the solid left behind. This is why basalt can form from mantle peridotite without the whole mantle becoming liquid. Partial melting extracts certain ingredients first. Magma is a selected liquid drawn from a more complicated solid. As magma rises, it can evolve. Crystals form and settle or remain suspended. Magma can mix with other magma. It can melt surrounding crust. Gases can accumulate. The chemistry of an eruption may therefore reflect a long underground history, not simply the first melt produced in the mantle. A lava sample at the surface is the final page of a journey through pressure, cooling, storage, and movement. Volcanoes also have plumbing systems. Dikes are sheet-like intrusions that cut across rock layers. Sills spread between layers. Laccoliths dome overlying rock upward. Batholiths are enormous bodies of crystallized magma exposed only after erosion removes the rock above them. Many magmas never erupt. They cool underground, becoming intrusive igneous rocks. For every visible eruption, there may be a larger hidden architecture. Granite is often the quiet remnant of magma that never reached the surface. It cools slowly underground, allowing crystals to grow large enough to see. Later uplift and erosion may expose it in mountain cores. A granite cliff can be the inside of an ancient magmatic system, revealed long after the volcano above has vanished. What once was deep becomes a landscape. Volcanic arcs may build continental crust. Some continental material is created and modified through subduction-related magmatism, adding lighter, silica-rich rock to the edges of continents. The exact growth of continents over Earth's history is complex, but volcanism and tectonics are central to it. Continents are not merely pieces left over from Earth's formation. They have been built, reworked, and preserved through planetary processes. Earthquakes can happen on volcanoes, under oceans, beneath mountains, and within stable regions, but their first explanation is always stress and failure. Rock can hold stress only to a point. When the strength of a fault is exceeded, slip occurs. The rupture may start in a small patch and spread. The final size depends on how much of the fault breaks, how far it slips, and how the surrounding crust responds. The beginning point of an earthquake inside Earth is called the hypocenter, while the point on the surface above it is the epicenter. Public reports often mention the epicenter, but the depth is just as important. A shallow earthquake directly under a town can be more severe locally than a deeper one of the same magnitude. Earthquakes are three-dimensional events, not dots on a flat map. Rupture direction can also shape shaking. If a fault rupture propagates toward a city, seismic energy may arrive more strongly and coherently, a phenomenon called directivity. The same earthquake can therefore affect different directions differently. This is another reason simple distance from the epicenter does not tell the whole story. The fault's geometry and motion matter. The duration of shaking matters too. Large earthquakes can shake for much longer than small ones because the rupture involves a greater fault area. Long-duration shaking can be especially damaging to large structures, slopes, and soft soils. It can also be psychologically powerful because the mind expects shaking to stop quickly. The Earth has its own timing, and large ruptures unfold across many seconds or minutes. Earthquake catalogs are historical records of seismicity. Modern instrumental catalogs are precise compared with older accounts, but written histories, archaeological evidence, and geological traces extend knowledge backward. Each region has a different depth of memory. Some have centuries of written earthquake history. Others rely mostly on geology. Understanding hazard means combining all available clocks. Induced seismicity shows that human activity can sometimes affect faults. Wastewater injection, reservoir filling, geothermal operations, mining, and fluid extraction can change stresses or pour pressure underground. Most induced events are small, but some have been damaging. This does not mean humans cause most earthquakes. It means faults can be sensitive to pressure and stress changes, and human actions can matter in particular settings. Reservoir-induced seismicity can occur when large amounts of water load the crust and seep into fractures. The added weight and poor pressure can change fault conditions. Again, the principle is not mysterious. Faults fail when stress and strength reach certain relationships. Water can alter those relationships. Geology is physical, and fluids are part of the physics. Volcanic unrest is sometimes ambiguous. A volcano can show earthquakes, deformation, or gas changes and still not erupt. Magma may stall. Hydrothermal systems may respond. Stress may shift without opening a path. This uncertainty is why observatories speak in probabilities and alert levels rather than absolute declarations. The aim is to communicate risk honestly as evidence changes. Alert levels are tools for decision-making. They summarize the current state of a volcano in language usable by officials, communities, aviation, and scientists. A raised level does not always mean an eruption is certain. A normal level does not mean a volcano is dead. It means current observations fit a certain range of behavior. Good communication is part of good science. Ash dispersal models use wind, eruption height, particle size, and weather forecasts to estimate where ash may travel. This is crucial for aviation and communities downwind. A volcano's impact depends not only on the vent, but on the atmosphere above it. Eruption and weather work together to determine where ash falls. The sky becomes part of the volcanic system. Rain can remobilize old ash years after an eruption. A landscape covered in loose volcanic material can produce lahars during storms long after the sky has cleared. River channels may be unstable. Sediment can clog reservoirs and change flood risk. Post-eruption recovery is therefore not only ecological, but hydrological and engineering related. The volcano continues to shape water after lava and ash stop. Ecosystem recovery after eruptions can be surprisingly creative. Some areas are buried deeply and begin again from bare surfaces. Others preserve roots, seeds, burrowing animals, or patches of surviving life. Wind, birds, insects, and water bring new material. At Mount St. Helens, recovery showed that disturbance is not uniform and that life returns through many pathways. A devastated landscape can become a mosaic of beginnings. Volcanoes create islands, and islands create evolution. Isolated volcanic islands can become laboratories of speciation as organisms arrive and diversify. Hawaii, the Galapagos, the Canaries, and other volcanic archipelagos show how geology and biology intertwine. The island begins as rock. Weather makes soil. Life arrives. Isolation shapes descendants. A volcano can eventually become a forest of unique forms. Black sand beaches are often made from basaltic volcanic fragments. Their dark color comes from iron-rich minerals and volcanic glass. Waves grind lava into sand, and the beach becomes a meeting place of eruption and ocean. A person walking on black sand is walking on cooled magma remade by surf. A violent beginning becomes a quiet shore. Volcanic glass forms when lava cools so quickly that crystals do not have time to grow. Obsidian is a familiar example, sharp, dark, and smooth. Ancient people used it for tools because it can fracture to a very fine edge. This is another link between volcanology and human history. A volcanic material became part of technology long before modern geology named it. Pumice is the opposite kind of volcanic surprise. Rock light enough to float, at least temporarily, because it is full of bubbles. It forms when gas-rich magma froths and cools quickly. Pumice rafts can drift across oceans after submarine or island eruptions, carrying small organisms and providing floating habitat. Even a bubble-filled rock can become part of dispersal and ecology. The smell near some volcanic areas comes from gases and hydrothermal reactions. Sulfur compounds can be sharp and memorable. Carbon dioxide can be odorless and dangerous in low places if it accumulates. This is why gas monitoring and restricted areas matter. A beautiful volcanic landscape may contain invisible hazards. Respect is part of visiting such places. Hot springs deposit minerals as water cools and degasses. Silica terraces, travertine, colorful microbial mats, and mineral crusts can form around thermal waters. The colors may come from microbes adapted to particular temperatures and chemistry. Hydrothermal landscapes, therefore, combine geology and biology. Heat from below meets life at the surface in vivid patterns. Geyser timing depends on underground plumbing, water supply, heat, and pressure. Old Faithful is famous for regularity, but even it varies. Other geysers are unpredictable, dormant, or newly active. A geyser is not a machine with a perfect schedule. It is a natural oscillator controlled by cavities, constrictions, steam, and groundwater. Its rhythm is stable enough to watch and variable enough to remain alive. The quiet science of earthquakes also includes microearthquakes. These small events help map faults and volcanic systems. They may be too weak to feel, but they show where rock is adjusting. In volcanic areas, swarms of tiny earthquakes can outline cracks or magma pathways. Small vibrations become a kind of underground drawing. Seismic instruments must be placed carefully. Bedrock sites reduce noise. Borehole instruments can avoid surface disturbance. Ocean bottom seismometers extend networks into the sea. Dense arrays can capture fine details of wave fields. The better the listening network, the more subtle the Earth becomes. A single seismometer hears one point. A network hears pattern. Citizen science sometimes contributes too. Felt reports help create intensity maps after earthquakes. People describing what they experienced can help scientists understand shaking distribution. Instruments are precise, but human observations still have value when gathered systematically. A sudden event becomes a shared data set, translated into maps that guide response and research. Satellite observations changed volcanology and tectonics by making remote deformation visible. Interferometric radar can compare repeated satellite passes and detect ground movement over wide areas. This has revealed inflation at volcanoes, subsidence from groundwater withdrawal, deformation after earthquakes, and slow motion along faults. The surface of Earth is moving in many places, often by amounts too small to see without space-based measurement. There are also earthquake lights, strange luminous reports sometimes associated with seismic events, but they remain difficult to study because observations are rare and conditions are poorly controlled. Some may have physical explanations involving electrical effects and stressed rocks. Others may be misidentified ordinary lights. A careful account should not turn such phenomena into certainty. The Earth permits mystery, but science asks for evidence. Volcanic acoustics is another field. Explosions, degassing, lava fountains, and pyroclastic flows can produce infrasound, sound waves below human hearing. Infrasound sensors help monitor remote eruptions and estimate activity. Like seismic waves, infrasound turns motion into a signal. The planet can be heard by instruments in frequencies the body never notices. Gravity measurements can also help monitor volcanoes and magma systems. If mass shifts underground, tiny changes in gravity may occur. These measurements are delicate and influenced by water, elevation, and other factors, but they add another clue. Volcanology is a science of many small clues, each incomplete alone and stronger together. After all these details, it helps to step back and see the two great processes as complete systems. A volcano is not only the cone visible above a horizon. It includes melting or stored magma below, pathways through rock, separating gases, groundwater, unstable slopes, and an atmosphere ready to carry ash. The mountain is the upper expression of a structure that begins far beneath it and continues into valleys, rivers, clouds, and soil. An earthquake is not only a dot called an epicenter. It is a rupture that begins at one patch of a fault and grows across a surface that may extend for kilometers or, in the largest events, hundreds of kilometers. Slip is uneven. The rupture has direction. Waves leave different parts of the fault at different moments. By the time shaking reaches a building, the signal already carries the shape of the fault and the history of its movement. This is why hazard maps have such specific shapes. Lava follows slopes. Lahars gather in valleys. Ash follows winds. Tsunamis enter low coasts and estuaries. Shaking changes with sediment, bedrock, distance, depth, and construction. The boundaries on a map are not drawn to make geology look orderly. They are attempts to translate a three-dimensional process into choices that can protect life. The same instruments that reveal these shapes also satisfy a quieter kind of curiosity. A seismometer used to warn of local shaking can help map the mantle. A satellite watching a restless volcano can also measure the slow bending of an entire region. Gas sensors, gravity measurements, field samples, and ocean bottom instruments all listen at different scales. Research and protection are not separate stories. They grow from the same wish to understand what the planet is doing. Other worlds make Earth's particular balance easier to notice. Mars built Olympus Mons, the largest volcano in the solar system, but it did not develop a modern network of moving plates like Earth's. Its giant volcanic provinces could remain over long-lived sources while the surface changed slowly around them. The Moon preserves ancient lava plains and impact scars because it has no rain, rivers, forests, or plate tectonics to rewrite them quickly. Earth is different because so many systems meet here. Interior heat moves rock. Water erodes mountains and enters subduction zones. The atmosphere carries ash. Life breaks down minerals and builds soil. Continents drift while oceans open and close. The surface is repeatedly erased, rebuilt, buried, lifted, and inhabited again. Its restlessness has costs, but it is also part of the long history that kept the planet chemically active and habitable. That does not mean every geological motion is beneficial or that danger should be romanticized. It means stillness is not the only form of stability. Earth has remained a home for life while changing continuously. Mountains have risen and worn away. Seas have appeared and vanished. Volcanoes have become forests. Fault scarps have softened beneath grass. Life has endured not on an unchanging world, but on a world whose changes usually unfold slowly enough for adaptation, memory, and renewal. The scale of that change can now narrow again toward the room around you. During one quiet night, the plate beneath a bed moves only a tiny fraction of the width of a hair. Mantle rock deforms even more slowly. The inner core grows by amounts no person could feel. Yet those small increments, gathered across millions of years, can move a continent from one climate zone to another and raise mountains from an ocean floor. Ordinary ground becomes more interesting once this is known. A granite step may be exposed magma that cooled far underground. A grain of sand may have passed through a mountain, a river, and an ancient sea. A dark beach may be lava ground down by waves. Clay may contain ash from an eruption whose volcano has almost disappeared. The surface beneath daily life is made from journeys too long for any human memory. The connection reaches into the body as well. Calcium, iron, salt, water, and carbon all belong to cycles that pass through rock, ocean, atmosphere, and living tissue. Shelter stands on crust. Crops grow in weathered minerals. Breath depends on an atmosphere shaped by both geology and life. The deep earth is distant in kilometers, but its consequences are present in almost everything close at hand. There is comfort in understanding a planet without pretending to control it. A subduction zone cannot be stopped, but it can be mapped. A volcano cannot be ordered to remain quiet, but its signals can be watched. A fault will not reveal an exact schedule, but buildings can be designed to move without collapsing. Knowledge does not make people larger than geology. It allows them to live on moving ground with greater care. And so the story returns to the contrast with which it began. The room is quiet, yet the planet is active. The floor feels still, yet the continent is traveling. Far below, metal flows around a solid inner core. Under dark oceans, basalt cools into new crust. Along distant faults, tiny earthquakes release stresses too small to notice. Somewhere, steam rises from warm ground, and somewhere else rain is turning old ash into soil. None of these processes needs your attention tonight. They have continued through nights without people, through ages before mammals, through oceans that no longer exist. The earth does not hurry, and there is no need to follow every plate, wave, or grain of ash to the end of its journey. It is enough to know that the pattern exists, heat moving outward, rock responding, landscapes changing, and life finding ways to remain. The ground beneath you is ordinary and extraordinary at the same time. It is a surface for rest, and the outermost page of a story written by pressure, water, heat, and time. For now, the page can remain still beneath you while the deeper chapters continue in darkness, slowly and patiently, exactly as they have for billions of years. Sleep well. Good night.